What? Calvin, this is a ridiculous question. So, Calvin, it turns out I didn't do number 15 in the last video. I stopped at number 14. My bad. We'll talk about that other thing later. Drop my paper. All right. So, number 15. We're going to take this one a lot further, which is why I've cleared off everything that's there. We're gonna find the molar mass, and then I'm going to ask about 4 more questions after that, because there's a lot you can do with this question. Hint, hint. Number 15. So I have the water. I'm dissolving an unknown mass in there. I got a delta T. Do we agree that the delta T is 3.3? It's usually water freezes at 0. Now it's freezing at 3.3, so it's dropped by 3.3. So let's just identify that our delta T is 3.3. And the Kf was given. It doesn't say if it's a non-electrolyte or not, and I really wish it had. I'm going to go ahead and tell you, for the sake of this question, this is a non-electrolyte. It will distinguish that on the test one way or the other. Maybe it gives you an I value to let you know. Yeah, Matt?
Could you explain why the thing with delta T, so it's the normal freezing point minus the new freezing point?
It'd still be final minus initial, right? And in this case, the final is, or it's 0 minus -3. Sorry. And then when you subtract, you get the positive. So either way you look at it, for the delta T's in either equation, it needs to be a positive value. Because on the other side of the equation, here's the equation, delta T equals I m Kf. Can anything on this side of the equation be negative? No. So this delta T always has to be a positive value. Otherwise, you're destroying matter or something like that. Yes, Lamia?
Can we do this both ways, like if it's a non-electrolyte and an electrolyte?
We're not going to do this one both ways, but you could. If it was an electrolyte, it would probably give you an I value. It'd say, I is equal to, 1.99, and you just plug that in for I. Or if it was something simple like sodium chloride, you'd say, well, I is probably 2. Yeah. All right?
This one doesn't have.
No, I meant to add into there, this is a non-electrolyte, into the question, so that you know that I is equal to 1. That's yeah. If it's a non-electrolyte, that means it's not dissociating, but it is dissolving. Pat?
What test do you give us when it's, like, you'll give us something that doesn't dissolve, so like,
Well, if it didn't dissolve, it wouldn't impact the freezing point.
yeah, but like, would you just like give a question like this, like something, we just have to know that it doesn't dissolve and say that?
No, I wouldn't do that to you. The question was, would I give you an insoluble salt or something like that, and then like try to trick you? Like, what's the freezing point? If you add 13 grams of, what's an insoluble salt? Lead iodide. 13 grams of lead iodide, how would the boiling point change? Trick question, not at all. Ha ha ha. No, I wouldn't do that. I'll give you something that's soluble, something that's like a group 1 or a group 2 ionic salt. I'll just give that to Wiley because he likes a trick question. Ari.
So a non-electrolyte doesn't have an I value, and an electrolyte.
A non-electrolyte has an I value equal to 1. As I, in my brain, the Van Hoff factor means how many ions does it break apart into, or how many pieces. And a non-electrolyte doesn't break apart, it stays as one big group. And the pieces are like whole glucose molecules, or whole ethanol or methanols moving around in there. All right? Haban? Well, if it's dissolving, that means it's being attracted to the water and it's making weak intermolecular bonds with the water. All right? So that's the general idea of dissolving. When things dissociate, those weak intermolecular bonds are strong enough to break the molecule or a compound apart into pieces. And so then you can have even more water molecules surrounding all those different pieces. So you can have something dissolve and be attracted to water that doesn't break apart. But if you have something that dissolves and breaks apart, then you have multiple pieces dissolving in. All right, so let's see what we can do with this one. We have 3.33. is equal to 1 times, we don't know the molality, but we do know K. K is 1.86. So we can solve for the molality. And then, oh, we do know part of this, though, don't we? What do we know of the molality? We know the kilograms. So I'm going to go ahead and say the kilograms down here, 0.090. Those are the kilograms of water. And when I solve for x, x is going to represent the moles of unknown. So this is 1.61 moles of the unknown liquid. So now we know the moles. They gave us the mass of this unknown, right? They gave us the mass, and one of the things we talked about earlier in the year is if you have the mass of a substance and you know how many moles, what can you calculate when you divide mass divided by its moles? Yeah, Kayla, good job. Molar mass. You can get the molar mass of the substance. So I'm going to take that mass, which was 10 grams of unknown, divide it by these moles, 1.61 grams divided by moles, gives me a molar mass of 62.1 grams. .161?
I got 1.71.
Oh, did I have my decimal in the wrong spot here? Oh, that happens. All right. I hope you're right, Melissa. All right, so Melissa says that I'm off by a decimal here when I wrote this down. She's right, Melissa's right. Thank you, Melissa. You've been confirmed by multiple sources. So, is this the molar mass then? I must not have written it down right when I was looking at my calculator. So, this is as far as this question asks you to go. I'm going to take this a step further, though. And here's some other information that wasn't given, but now it's going to be given. So, somebody tells you that this is 19.3% carbon by mass, 51.5% oxygen, and 29.2% hydrogen. And so these are the percentages of each element by mass. If it wasn't by mass, they'd probably give you the mole fraction if it was by moles. These are the percentages by mass, and I'm going to apply each of those to this 62 grams, and that'll tell me how many grams of each element are in there. And once I have grams, I can convert grams into moles and figure out the formula. All right, so let's just do that. I'm going to apply those grams, so 62.1 times 0.193 ends up being about 24 grams of carbon. 62.1 times 0.515 ends up being about 32 grams of oxygen. And then 62.1 times 0.292 ends up being, where is it? About, where'd it go? There it is. About 6 grams of hydrogen. Is that right? Yeah.
When I did carbon, I got
11.98? Wait, maybe I did something wrong here. Let's try this again. Maybe I didn't write down the right stuff here, or I'm looking at the wrong formula. What'd you get? 11.98? What'd you get for oxygen? 32? And for hydrogen? Say again? 18? I feel like there's something wrong here. Say that louder. All right. Let me pause this for a second. So I had a typo here. S was supposed to be 39.3. That was supposed to be 9.2. My bad. But so I took the 62.1 0.1 and applied those percentages, and I got 24, 32, and 16. If I have 24 grams of carbon, how many moles is 24 grams? Yeah, that's 6. But if I have 24 grams of carbon, that would be 2 moles of carbon. 32 grams of oxygen would be 2 moles of oxygen. And then 6 grams of hydrogen would be how many hydrogens? 6. And this is a formula for something called ethylene glycol, which is really good at lowering boiling points. It dissolves pretty well in water. But what I was trying to get to is you can apply those percentages to a molar mass, and then you get the grams of each substance. If you divide these grams by their molar mass, you can actually work out a formula. And we don't know the name of that formula in our organic nomenclature, but we could figure it out. Wiley?
So would you leave it as that, or would you have to simplify the today?
Say again?
So would you leave it like that?
Yes, because this is equal to the molar mass of that. This is the molecule's mass. The empirical formula would be the reduced form, COH3. But that empirical formula might not be a real molecule, might not be able to be formed and put together with the right bonds. Haban?
So on the AP test, is it right, like, better to go through this or using an empirical formula?
You can do it either way. If you have the molar mass, I think it's a lot easier just to apply the percentages right to the molar mass, because you cut out all those little steps of dividing by this or multiplying by that. Because if you have the molar mass and you apply the percentages to that, it takes you right to the molecular formula. And if you have the molecular formula, it's easy to find an empirical formula. You just divide by the common denominator. Yeah, I divided each of these by, so this one I divided by 12, by 16, and by 1, by their molar masses. That tells me how many moles of each are in the compound. Okay, we have another freezing point depression one. Number 16. It's pretty much the same question. The one thing I want to point out, though, is when you do this delta T, when you solve for delta T, you get a delta T that's 5.4. So, you've gone through the whole process. You're like delta T equals I, M, K. We're freezing. Plug in all the values. Solve for the molarity. It's a non-electrolyte, so I is 1. And you get a delta T that is equal to 5.4. What does delta T represent? Melissa? It represents the change in temperature. Is it going to go up or down? Freezing point always goes down. Is that your question?
Yeah, how do you know what it's at?
If it's a freezing point, the freezing point always goes down. The boiling point always goes higher.
Oh, you just have to know based on because you're adding.
Yeah. So instead of being a negative 114, it's actually going to drop another 5 degrees, which is negative 120. So it's going to drop 5.4 more degrees. Say again? Oh, well, we have the constant, right? So we have K. We need to figure out the molality. So we have the moles divided by the kilograms of solvent. So I converted 50 grams of glycerin into moles and then divided it by 0.2 kilograms of solvent to get that molality. It says it's a non-electrolyte, so I doesn't matter. It's a 1. Multiply those together, you get a delta T of 5.4. Let's see, number 17 is actually the pi equation. The pi equals the molarity R times the temperature. So we have to have the molarity of the substance. They have given us a volume of the solution. So we don't have to do any fancy work for the volume because it's already of the entire solution. So I have 0.250 liters for my volume. And what goes on top? The moles? Well, we don't know the moles. We know R is 0.0821 or 206 if you prefer. We have 298. And we have the pressure. What's the pressure here? 1.2? And so the only thing missing right now is the moles that's being dissolved into it. The osmotic pressure is represented by pi. So the moles I have are equal to 0.01226. How are we going to find the molar mass, though? Yes, this molarity is moles divided by liters.
So you can take the moles and divide it by the moles.
Strike that, reverse it. Take the grams
Divide by the moles.
divided by the moles, right. So I'm going to take the grams, those 33.2 grams divided by 0.01226 moles, and I would have the molar mass of this substance, which is somewhere on this piece of paper. Oh, wow, this is a huge one. 2,700 grams per mole. That must be a gigantic molecule, some very long organic chain of some sort.
Wait, so you can have something like that?
Well, DNA has a ridiculous molar mass. Yeah, it's a never-ending, not never-ending, but it's a huge chain, right? How many millions of carbons are in a DNA chain? 1,000,000 times 12 is a pretty big molar mass. Yeah. It's technically all one molecule, so I don't think anyone ever does molar mass stuff with it because it's constantly breaking and falling apart. Calvin?
Would we need to take anything with that 2,700, like turn it into a formula of sorts to deal with stuff?
If we had a smaller molar mass, a more reasonable one, like we did a second ago with percentages, yeah, you could. This one, though, is just ludicrous. I mean, it's this big, it's probably got all sorts of elements in it, not just carbon, hydrogen, and oxygen. Probably get nitrogen, sulfur, phosphorus, a whole bunch of things. Haban?
How would this question be different if it was an electrolyte?
If it was an electrolyte, then I would represent the number of ions, right?
That would define if it was an ion or
Yeah.
Would the M stand for molarity?
In this case, the M does stand for molarity. Yep. All right, let's go to 18. 18, George is making spaghetti. How much does the temperature change? This is the delta T, KB, molality, and an I in here for fun. Do we need the I this time?
Yes.
Yeah, we have a salt, and sodium chloride usually breaks apart into two ions. So I'd say I is equal to 2, K is 0.52, and I've got to get a molality in here. This happens to be 58 grams of salt, which is 1 mole of salt. We have 1 mole of salt, and we have 4.01 kilograms of water. So Sophia, you must be boiling your spaghetti noodles right now. Sophia likes to make spaghetti. At least in my 7th period she does. So I've got my delta T. This delta T is very small. This delta T ends up being 0.26. Melissa, what does that mean? That this is the boiling point. Is it going up or down by 0.26? It's going up by 0.26. So instead of boiling at 100, it's going to boil at 100.26. Not that impressive, is it? That's not very much salt. If Sophia really wanted to raise the temperature, she'd have to add a lot of salt. And yes, Riley, the salt would go out with the water. We always get in this argument about how much the salt affects the taste, and I'm just not going to give in. All right. From here on, we have a bunch of definition style things, just conversation. The formation of a solution where the process is endothermic can be spontaneous, provided there's an increase in disorder. I kind of used my delta G stuff. If it's endothermic, H would be positive. So the only way it's a spontaneous is if we have a gain in entropy that overcomes it. Right? That negative T delta S has to be larger than the enthalpy. That stuff's not going to go away. Isn't that awesome? No, don't make that face, Priya. I saw that. So you have to increase in disorder. And number 20, the phrase like dissolves like refers to the fact that polar solvents dissolve polar and nonpolar dissolves nonpolar. I think we've seen that a dozen times.